Welcome back to Larry's Classroom. Today we're going to talk about a loaded voltage divider. We'll start with a power source and three resistors. 1, 2, 3. We got a 120 volt supply, negative, positive, so we're going to have our electron current flow counterclockwise around this loop. 3 resistors, R1, R2, R3. Now we're going to have some loads on these. We're going to have load A, just going to put an A there. And this is going to be 20 volts. 20 volts at 35 milliamps. Another load, load B. And this is going to be 50 volts at 60 milliamps. 65 milliamps. No, it's 60 milliamps. 60 milliamps. And we have one more load, load C, which will be 120 volts, 200 milliamps. So we've got a 120 volt supply, we've got 3 voltage divider resistors to distribute the voltage as 20 across A, 50 across B, and 120 across C. We can see that C is hooked directly across the load, so it doesn't really need no voltage division. But load B, 50 volts, so there'd be 50 volts across the combination of R1 and R2. So we got a voltage divider formed by R1, R2 divided by R1, R2 plus R3, and load A, 20 volts at 35 milliamps, which is going to be connected across R1, and it will form, these 3 resistors will form a voltage divider of R1 over R total, which R total is R1, R2, and R3, to divide this 120 volts down to the 20 volts. Now let's look at what the voltage is across each resistor. I'm going to put the voltage right here. This is the negative to positive, so this will be plus 20 volts right here. And this 50 volt supply is across here, so we're going to have plus 50 volts here. And up here at the top of R3 we have plus 120 volts. We're going to put a little ground symbol here just for a reference point. That's how we're measuring our voltage from ground to this point here between the junction of R1 and R2. We'll see 20 volts. From ground to the junction of R2 and R3, we'll see 50 volts, which is what we need for the load B. And from ground to the junction, the top of R3, we'll see 120 volts, which is what we need for load C. Let's calculate the voltages across each of these resistors first of all. And we're going to call these, I'm going to say V1, no, V3, excuse me. Across R3 is going to be V3. Across R2 is going to be V2, and across R1 is V1. Well, V1's basically given to us. We want 20 volts, right? Now across the combination of R1 and R2, we need 50 volts, but we have 20 volts across R1. So let's determine what our voltage will be here. V2 is going to be equal to V1. Well, it's going to be equal to, yes, excuse me, VB, the voltage for B is going to be equal to V1, the voltage across R1, plus V2, the voltage across R2. Well, VB for load B, 50 volts, and V1 is 20 volts, plus V2. Well, what do we need V2 to be? Subtract 20 from both sides, 30 volts equals V2. So let's put that up here. V2 equals 30 volts. And you can see that 20 plus 30 will give us the 50 we need for B. 20 across V1 will give the voltage we need for load A. And we could calculate V3. We could do it two ways. We could say that V3 equals 120 volts, which is, well, no, V3 equals VC, 120 volts, plus V1, no, get this right. VC will be equal to V1 plus V2 plus V3. Let's write that in here. V1 plus V2 plus V3. So there's our formula to find out. Well, VC is given. We've already got V1 and V2, so let's put in there. VC equals V1, which is 20 volts, plus V2, which is 30 volts, plus V3, which we do not know yet, and VC we have to be 120 volts. So let's put that in there. So we've got three voltages, one unknown voltage. Well, we're going to subtract 20 and 30 from both sides. Well, 120 minus 50 is 70 volts equals V3. So let's put that up here. So we've got the voltage across each resistor. And we did that using the basically voltage total equals voltage 1 plus voltage 2 plus voltage 3. And our voltage total was 120 volts. So we calculate each of these voltages using the voltage total formula for 2 resistors, for 3 resistors, and so on. Well, voltage total equals V1, which is 20 volts, plus V2, which is 30 volts, plus V3, which is, I'm going to write that up there, 70 volts we just calculated. Well, 20 plus 30 is 50 plus 70 is 120 volts, which is exactly what we expected, because we're supplying 120 volts, and that's what we need for the load C. I'm going to go ahead and I'll leave these calculations up here for right now. Let's work on calculating the current through each resistor. Oh, well, I ain't there yet. We want to, let's figure out the total current for the loads. I of the loads equals IA, the voltage for load A, plus IB, the current for, current, not voltage, IB, the current for load B, plus IC, the current for load C. Well, let's add those up. Let's just do it right here. I load equals IA, 35 milliamps, plus IB, which we got over here, 60 milliamps, plus IC, which is a load C, which is 200 milliamps. If we add that up, what do we get? 35 and 60 is 95 plus 200. We get 295 milliamps. So we've got total load for our loads that we're going to supply power to of 295 milliamps. Now we like to have even if the loads are all disconnected, we want some voltage flowing through these resistors to establish our, just to give us some stability. So, and we call that the bleeder resistance. And we like IB. We're going to call this IBL, I bleeder. We want that to be approximately equal to 10% of I load. Well, 295 milliamps. We round that to 300 divided by 10. So it's going to be about, we're going to set our IB equal to 30 milliamps, or IBL. I'm going to write that over here. IL, we're going to put this here, 295 milliamps. And IBL, which we'll call our bleeder current. And this is current that flows through the voltage divider, that does not flow through the loads that we're supplying from this voltage divider. And that's, we're going to use 30 milliamps. So we want to figure out the current through each resistor. Well, what's our current? None of our load currents, current from A goes up through R2 and R3, current from load B goes up through R3, and current through C goes directly back to the source. So none of our load currents go through R1. So we're going to call this I1, current 1, equals the bleeder current, which we're going to set to be 30 milliamps. Now, so we're going to put 30 milliamps right here. Yeah. 30 milliamps, I'm going to put a little arrow for that 30 milliamps. So what we're working on here is calculating the current through each resistor. Well, we have our current summation formula. IT equals I branch 1 plus I branch 2 plus I branch 3, so on, for however many we have. So we've got this current here from load A flowing that way, which is 35 milliamps. So we need to figure out how much I2 is. We want to find I2, so we want to find the current flowing through R2. Well, by this current, it's going to be I2 will equal I1, which is just 30 milliamps, plus, we'll call this IA, 35 milliamps that's coming off of load A, plus IA, so that's going to be I1, which is 30 milliamps, plus IA, which is 35 milliamps. That gives us 60 milliamps. So we've got 60 milliamps flowing through R2. We're going to write that down here. We're going to call that I2. 60 milliamps. Now don't confuse that with the arrow. I'm going to write these over here. I2 equals 60 milliamps. Just to avoid the clutter that's coming up over here. Get that out of there. And let's go ahead and get this I1 of 30 milliamps that we wrote here out of there too. And let's put it over here. We're going to say that I1 equals 30 milliamps. And we did that by summing IA plus I1 to get I2 30 and 35, we use this formula here. We're going to do a similar calculation for I3. We want to find I3. Well, what's that going to be? We got IB right here equal to 60 milliamps, right? I got something wrong here. This is 65 milliamps. 30 plus 35 is 65. And I wrote down 60, which is not correct. 30 here, 35 here, 65 milliamps. And we'll put the 65 right here too, so we don't get too confused. So we got IB of 60 milliamps. So we can calculate I3. We can do two ways. It'll be I2 plus IB, or we could say that I3 would be equal to I1 plus IA plus IB. We should get the same answer either way. I1 plus IA plus IB. I1 goes all the way through all of them. IA goes through R2 and R3. IB goes through just I3. So let's calculate this both ways. Make sure we do get the same answer. I2, 65 milliamps. And we're going to add to that IB, load B. This is BL. No. IB. IB is load B. IBL is equal to I1. The bleeding current. I2, 65 milliamps. IB, load B, plus 60 milliamps. And that is 125 milliamps. Now let's make sure we get the same thing this way. I1 was 30 milliamps. IA was 35 milliamps. Plus IB, load B, 60 milliamps. And 30 plus 35 is 65. Plus 60 again, 125 milliamps. So let's write this right up here, I3. $125 milliamps. So we've basically calculated every current. We've calculated every voltage. The voltages we did by looking at the voltage needed to supply each load, and we then found voltages at each point here, and we did voltage difference to get the voltage drop across each resistor. We got 70 volts across V3. We have 30 volts across V2. We got 20 volts across V1. Well, 20 plus 30 is 50, plus 70 gives us 120, which matches our source impedance, our source supply, our voltage supply. Now we need to calculate each of these currents. So I'm going to erase some of this stuff here, give us some room, or each one of these resistances. And we're going to use our tried and true resistance formula from Ohm's law that says resistance equals voltage over current. So R1, let's start by calculating R1. Should equal the current through R1, or the voltage across R1, which is basically V1, divided by the current through R1, which is I1. Now we'll substitute some values in there. V1, 20 volts across R1. Now the current, we got 30 milliamps, but 30 milliamps is also equal to 0.030 amps. And basically, that's 30 thousandths of an amp, and this is a milliamp is a thousandth of an amp. We have 30 milliamps, and this number 0.030 is basically 30 thousandths. And the reason we did that, we want our result in ohms. We want the source voltage in volts and the current in amps to get it in ohms. If we use milliamps, we get k ohms, and we don't really want k ohms right now. Anyway, if we take the 20 volts divided by 0.03 amps, that comes out, rounding to the first decimal place, of 666.7 ohms. So let's write that up here. Let's R1, let's use black. We'll start with black for the equals 666.7 ohms. And let's calculate the resistance of R2. We're just use the same formula. This guy right here. Ohm's law, resistance equals voltage divided by current. R2, voltage 2 divided by current 2. Voltage 2, which is the voltage dropped across resistor R2, not the total from the ground to there. The voltage drop across R2 we calculated to be 30 volts. So we have 30 volts. And I2, 65 milliamps through that, which is 0.065 amps. We'll convert it to amps so that we have the proper units to get a resistance in ohms. Well, I'm rounding all these, so I'm going to put the little squiggly equal sign. For something like this, you wouldn't need to carry it out to 10 decimal places. So that one might not even, we come up with 461.5 ohms. So let's write that up here too. R2 equals 461.5 ohms. Let's do R3. Same formula, Ohm's law, resistance equals voltage times current, but we want to use voltage 3 and current 3. Voltage 3, the drop across R3 after we subtracted the total voltage minus the drop across R1 and R2, we come up with 70 volts. 70 volts. And the current through R3 was I3, which we found to be 125 milliamps. 0.125 amps. Which is 1/8 of an amp. But if we do the division on the calculator, we end up with 560 ohms. So let's write that up there by R3 too. So we've made use of everything we've been doing with Ohm's law, dividing, current, so on. We've used our voltage summation formulas to find the voltage drop across each particular piece of the voltage divider. We found 20 volts, which was this voltage. We found 30 volts, which was 50 minus 20. We found 70 volts here, which was this 120 minus the 50. We did that two ways, but it came out the same answer. So we got all the voltages. We designed this thing to use a 30 milliamp bleeder current, which is roughly 10% of the total of the load current. And so we had that current, which we chose. These were given to us by the loads that we were supplying. Well, so we had this chosen bleeder current, which we used for I1. 30 plus 35 summed together gave us 65 here. For I2, 65 plus 60 summed together gives 125 for I3. So we found a set of resistors that will do what we desire for these particular application. Now let's think about this now. This will work well as long as each of these currents are pretty consistent. Now let's think about what happened if the current changed. If this current for IA increased, we'd have more current for I2 and more current for I3, and that would cause a greater voltage drop there. That would lower the voltage across R1. That would be lowering the bleeder current. But the worst impact of it is we would no longer have our 20 volts. We'd have something less than 20 volts. If this current got to be less, then we would have less voltage drop, which would cause that thing to go up to maybe 22 volts. That would increase the current here. So changes of current are going to impact everybody. Less current here is going to lower that drop, which is going to reduce this drop, which will make the voltage go up in here. They interact. This type of a setup is only practical if you have really constant loads. Now, one situation where you might see using something like this is you're setting biases on different sections of your amplifiers and other circuits, which are low current loads, so it doesn't change, it probably ain't going to change much. You're mostly interested in the voltage. So this wouldn't be real practical for run loads that varied, but if there were loads that the current requirements were very consistent, it would be okay. Now you remember earlier we worked on a voltage divider, and in that one we wanted to get greater stability, so rather than a 10% bleeder current, we did an example where we used about 1,000% bleeder current, which is 10 times the load. Well, if we wanted to get 10, and that gave us, we saw that was more stable regulation as if these currents in the loads varied. Well, here we had a total load current of 295 milliamps. We'll round that to 300 milliamps, or 3/10 of an amp. If we wanted to set this bleeder to 10 times that, we'd have 3 amps of bleeder current. Well, 3 amps plus the 0.3 amps of load, 3.3 amps, so we need a power supply capable of at least 3.3 amps rather than one that only has to put out 325 milliamps. So we need a power supply capable of in excess of 3 amps rather than one that only put out 1/3 of an amp. Plus, with that 3, these resistors would change value because of the higher current too. But the additional current through here, let's just say we got 3 amps through there. 3 amps times 120 volts, that gives us 360 watts. We would need these 3 resistors combined to just to handle the bleeder current. They have to be dissipating 360 watts. Them are some pretty heavy resistors. In this case, plus they would have to dissipate the power from each of these loads too, which with the 10 times factor would be less. But in this case, we got a bleeder current of roughly 1/10 of the total load current. So we got 0.03 amps. and we multiply that times 120 volts, that's, to take care of the bleeder current, we only need 3.6 watts here. Plus, we'd have to dissipate whatever went through here, which in this case would be a greater amount, but we might need a total of maybe 10 watts. So we maybe need some 3-watt resistors. But you can see that if we increase the bleeder current to be 10 times the total of the load, we need big, heavy, power dissipating resistors, which means you're wasting a lot of energy, and it would probably be better to design separate voltage regulators for each of these sources. And you know, load C, you wouldn't really need one because that's your source voltage. Now what you could do is, and this might be the way you do it, you might use these voltages to be a signal to adjust the voltage of an adjustable voltage regulator for A and an adjustable voltage regulator for B. Because the signals would be low current, and it wouldn't swing this thing around really hardly at all. But we've utilized pretty much Ohm's law, we've utilized our voltage total formula, we've utilized our current summation formula, we've used our power formula. Well, we didn't really use the power formula. I guess we did a little bit here, but that was just kind of looking at. But if we really wanted to build it, we would have to use the power formula to determine how heavy of each of these resistors would have to be. We just did a quick talk with it to see that we would need some pretty heavy resistors if we went with the 10 times bleeder current rather than the 1/10 bleeder current. So this circuit probably wouldn't very often be used to drive loads like this, but still a good workout to understand how these things can be done. Anyway, I think we've kind of covered that. Thanks for coming back. Be sure to like and subscribe, and I hope that you've found a book of some sort and are doing some practice problems in addition to the ones that I do on the board to help you with. It always helps to practice to reinforce these ideas into your mind and help them stick with you better. Anyway, thanks for coming. Till the next time, keep on learning.